85% of the matter in the universe is made of dark matter. But to date, we do not know what dark matter is made of. Now researchers have made an experiment which could allow them in the future to unveil this mystery. Physicists at the National Institute of Standards and Technology (NIST) have linked together or entangled the mechanical motion and electronic properties of a tiny blue crystal, giving it a quantum edge in measuring electric fields with record sensitivity that may enhance understanding of the universe. The quantum sensor consists of 150 beryllium ions, electrically charged atoms, confined in a magnetic field, so they self-arrange into a flat 2D crystal, just 200 millionths of a meter in diameter. Quantum sensors such as this have the potential to detect signals from dark matter, a mysterious substance that might turn out to be, among other theories, subatomic particles that interact with normal matter through a weak electromagnetic field. The presence of dark matter could cause the crystal to wiggle in telltale ways, revealed by collective changes among the crystal's ions in one of their electronic properties known as spin. As described in the journal Science, researchers can measure the vibrational excitation of the crystal, the flat plane moving up and down like the head of a drum, by monitoring changes in the collective spin. Measuring the spin indicates the extent of the vibrational excitation, referred to as displacement. This sensor can measure external electric fields that have the same vibration frequency as the crystal with more than 10 times the sensitivity of any previously demonstrated atomic sensor. Technically, the sensor can measure 240 nanovolts per meter in 1 second. In the experiments, researchers apply a weak electric field to excite and test the crystal sensor. A dark matter search would look for such a signal. The researchers say that the ion crystals could detect certain types of dark matter. Examples are axions and hidden photons that interact with normal matter through a weak electric field. The dark matter forms a background signal with an oscillation frequency that depends on the mass of the dark matter particle. Experiments searching for this type of dark matter have been ongoing for more than a decade with superconducting circuits. The motion of trapped ions provides sensitivity over a different range of frequencies. The research group has been working with the ion crystal for more than a decade. What is new is the use of a specific type of laser light to entangle the collective motion and spins of a large number of ions, plus what the researchers call a time reversal strategy to detect the results. The researchers used microwaves to produce desired values of the spins. Ions can be spin up, often envisioned as an arrow pointing up, spin down, or other angles, including both at the same time, a special quantum state. In this experiment, the ions all had the same spin, first spin up and then horizontal. So, when excited, they rotated together in a pattern characteristic of spinning tops. Crossed laser beams with a difference in frequency that was nearly the same as the motion were used to entangle the collective spin with the motion. The crystal was then vibrationally excited. The same lasers and microwaves were used to undo the entanglement. To determine how much the crystal moved, researchers measured the ion's spin level of fluorescence. Spin up scatters light, spin down is dark. In the future, increasing the number of ions to 100,000 by making 3D crystals is expected to improve the sensing capability 30-fold. In addition, the stability of the crystal's excited motion might be improved, which would enhance the time reversal process and the precision of the results. The researcher says that if they are able to improve this aspect, this experiment can become a fundamental resource for detecting dark matter.